everyone, welcome to IIT-JAM in chemistry tutorial number 41, and this is part 3 of lecture number 2 of the physical chemistry chapter solid state. In part 1 of lecture number 2, we have learned about the lattice vectors and crystal directions. And in the second part of this lecture, Miller indices and reciprocal lattice were discussed. And now in the third part, under the same subtopic, elementary applications of vectors to crystal systems, we are going to discuss about the symmetry operations. In symmetry operations, actually they involve some transformations. It is such a transformation that can leave the crystal lattice unchanged, and these transformations can be done by some mathematical operations represented by the vectors. Now the crystal lattices have 4 types of external symmetries and 2 types of internal symmetries. These are number 1, center of symmetry, number 2, plane of symmetry. Center of symmetry is denoted as I, small letter, or 1 bar. Mirror of symmetry, mirror plane is denoted as small letter m, or 2 bar. Now axis of symmetry or rotation axis or proper axis of rotation, there are 4 types, 2, 3, 4 and 6. And improper axis of symmetry or inversion axis, they are 3 types, 3 bar, 4 bar and 6 bar. Now among the internal symmetries, one is glide plane, another is screw axis. Now let's start from the external symmetries. First, center of symmetry, which is small letter I or 1 bar. So if every face of a crystal has another identical face at an equal distance from a central point, then this point is called the center of symmetry, denoted as small letter I or 1 bar. Now let us elaborate. Suppose this is a crystal and this is the face. So let us start our journey from this point, and this journey ends here. So this point is repeated here, and this point is the middle of this path length. Now if you start your journey from this point and pass through this center, and the journey would end here after from here to here, the same distance here to here, then here this point is repeated again. So similarly, from any part of this crystal or unit cell, you can get repetition if you start your journey from any point and pass through this single point, and this is the center of symmetry. The same thing is repeated here also. If you start your journey here to here, from here to here, then this is the middle point. Now start your journey from this point, pass through this center and end to the same distance, then this point is again repeated. So this is the center of symmetry. Now the characteristics of the center of symmetry is each and every out of these 7 crystal systems has 1 center of symmetry. So if you have 7 crystal systems, and each of them, all of them, has 1 center of symmetry. Now stereographic projection, if this O plus is above the paper, above the plane or above the paper, then or this solid disk is above the plane, then O negative is below the plane, or this empty circle denotes below the plane. In that case, I, small letter I or 1 bar, is represented as, if this is the lattice point which is above the plane, then after having passing through this center of symmetry, it is repeated here. So this O plus becomes O minus, or this solid disk becomes empty circle. This is stereographic projection. Now move on to the second symmetry element, which is the plane of symmetry. It is denoted as small letter m or 2 bar. When a crystal is divided by an imaginary plane into 2 halves, such that one is the mirror image of the other, then that imaginary plane is called the plane of symmetry, denoted as small letter m. So this is the picture of a cube, and we have 9 sets of pictures here, and each cube has different type of plane of symmetry, and you can see that this colored planes are the planes of symmetry, and through this plane, if you take the mirror image, the same portion is repeated. Okay, so this cube can have this way 9 types of planes of symmetry, and the stereographic projection is like that. If this is the plane of symmetry and this is the lattice point, then on the same paper on the same plane it is repeated. If the plane of the paper is the mirror, then the empty circle becomes solid line, or the solid disk becomes empty circle. Okay, move on to the third symmetry element, which is axis of symmetry. So, and there are 4 types: 2, 3, 4 and 6. 2-fold, 3-fold, 4-fold or 6-fold axis of symmetry. In general, if they are written as n small letter, then it is n-fold axis of symmetry or n-fold rotation axis. So an n-fold rotation axis is one for which a rotation through twice pi by n leaves the appearance of the crystal unchanged. That is, if you have 2-fold axis of symmetry, 2 pi is 360 degree. So 2 pi by 2, that is 180 degree. So you have to rotate the crystal by 180 degree. For 3-fold axis of symmetry, you have to rotate by 120 degree. For 4-fold, 90 degree. For 6-fold, 60 degree. For n equals to 4, this is 4-fold axis of symmetry. For a cube, this number is 3. This is 3-fold axis of symmetry. For a cube, it has 4 sets of 4 number of 3-fold axis of symmetry. And what about 2-fold axis of symmetry? For a cube, it has total 6 number of 2-fold axis of symmetry. Okay, for n equals to 2, it is called a dyad. For n equals to 3, it is called a triad. For n equals to 4, it is called a tetrad. And a cube does not have a 6-fold axis of symmetry, but if some other unit cell or crystal has 6-fold axis of symmetry, then for n equal to 6, it is called a hexad. Stereographic projections are like this. This is for 2-fold axis, this is for 3-fold axis, 4-fold axis, 6-fold axis. And the symbols, look, for 2-fold axis, this is this is drawn as an ellipse, a solid ellipse. Okay, this is a solid triangle, this is a solid square or diamond shape, and this is a solid hexagon. Okay, and you have marked one thing. Look, in case of a cube, the number of 2-fold axis of symmetry is 6 and the multiplication of 2 and 6 is 12. Now look at the next fact. The 3-fold axis, a cube can have 4 number of 3-fold axis, and the multiplication of 3 and 4 is 12 again. How many 4-fold axis of symmetry does a cube can have? It is 3. So again the multiplication is 4 into 3 equals to 12. So if you are asked that a cube can have how many 6-fold axis of symmetry, 2-fold axis of symmetry, then just simply divide 12 by 2. The answer is 6. If you are asked a cube can have how many 3-fold axis of symmetry, then divide 12 by 3 and the answer is 4. Okay, so this is the amazing fact. And this axis of symmetry, provided all of them are the proper axis of symmetry. Okay. Now inversion axis, 3 bar, 4 bar and 6 bar. It involves 2 steps. Okay, the first step is rotation by twice pi by n about the n bar axis, and secondly inversion through the center on that same axis. Okay, look at this. This is the 2 bar, actually the mirror plane. 2 bar is mirror plane, we have already marked, and 1 bar is center of symmetry. We know that. Let us focus on 3 bar. Okay, so this is the top face, this is the bottom face, this is the right face, this is the left face, this is the front face, and this is the back face of this cube. Okay, so let us take for example the top face of that cube, then rotate it by 120 degree, because this is 3 bar, so 2 pi by 3 means 120 degree, so rotate by 120 degree. This top face takes the place of the back face. Now if this face is inverted along the center of symmetry, then it comes to the front face. So the 3 bar improper axis of symmetry rotation for the top face becomes the front face. Similarly, for this octahedron, this is the right top face. Okay, this is the right top face. Now rotate it by 90 degree, because this is 4. So 120 by 4 is 90 degree. So 4, it becomes the top back face. Now after inversion through this center, it becomes the bottom front face. Okay, bottom front face. All they are shaded well. Similarly, this is a hexagonal bipyramid. So this face is repeated here after the 6 bar operation, and here the 2 bar operation, simply this is actually nothing but the mirror plane. After twofold, that means 180 degree, the right top face goes to the left top face, and after inversion it goes to the right bottom face. Okay, so this is nothing but the mirror plane, and for I it is rotated by 360 degrees. So here, and after inversion it comes here, that is the left bottom face. So that is, this is nothing but this center. So this center of symmetry. That is why center of symmetry I is denoted sometimes as 1 bar, and mirror plane is sometimes denoted as 2 bar. Stereographic projections, these are the symbols for 3 bar, this is the symbol for 4 bar, and this is the symbol for 6 bar, and these are the projections. Okay, just have a look, you will understand, and you must have to draw in paper by yourself, then it will be more clear or more prominent to you. So I am holding this for few seconds, just have a look, then do it on paper by yourself. Okay, now come to the internal symmetry. So the fifth symmetry element, fifth and sixth symmetry elements are internal symmetries. Okay, number 5 is glide plane. Glide planes may be A, B, C, N and T. There are overall 12 number of glide planes. Okay, if the glide plane is A, then it can be either A perpendicular to B or A perpendicular to C. Now I have said A perpendicular to B, but actually it is pronounced as A glide perpendicular to B. The symmetry element A glide perpendicular to B is pronounced as A glide perpendicular to B. So take it into account that it is pronounced as A glide perpendicular to B. Okay. So for A glide perpendicular to B, it involves 2 operations. Number 1, first operation involves reflection through a plane perpendicular to B axis, and secondly translation by A axis by half unit. Okay, translation through A axis by half unit. If you can have a look on the stereographic projections, then it will be more clear. Now you take as for example A glide perpendicular to B. So B is the mirror plane. Okay, B is the mirror plane. That means the plane is perpendicular to the B axis. So which is B plane? B plane is that plane which is perpendicular to the B axis. So this is the reflection plane, and A axis is the gliding axis, because you have to glide along A axis by half unit, sometimes 1/4 unit, whatever is required. Okay, here for A glide perpendicular to B, you have to translate by half unit. Okay, so the stereographic projections of A glide perpendicular to B and A glide perpendicular to C glide perpendicular to B. So this is the A axis and this is the C axis. A axis means X axis, C axis means Z axis. So what about the Y axis or B axis? This, if this monitor is the plane of the paper, then the axis is just perpendicular to your monitor of your mobile or computer or your paper. Okay, now this is the lattice point. So this is denoted as O plus. If you take the reflection of this point, it will become O minus, because the plane is actually the plane of the paper. Okay, and this O minus, after having glided along A axis by half unit, it comes here. So O minus is repeated here. So if this lattice point is repeated here, then this crystal lattice must have a internal symmetry element A glide perpendicular to B. After operating this O negative, it again is repeated here. It is appearing as O positive here. But if the symmetry element is C glide perpendicular to B, then you have to just glide along C axis. Instead of A axis, you have to glide along C axis. So this lattice point is repeated here and this lattice point is repeated here. So this way A glide perpendicular to B and C glide perpendicular to B are written. So if the B axis can have two glide planes, then A axis can also have two glide planes and C axis can also have two glide planes. So in total, from this we can have in total 6 glide planes. Now we have 6 more glide planes left, because I have said already we have 12 number of glide planes. Okay, so let us move on to glide planes N and D. So what about the operations in case of N and D? Let us take N glide perpendicular to A. Okay, so you can assume that there must be N glide perpendicular to B and N glide perpendicular to C also. So let us start with the example N glide perpendicular to A. So what about the operations here? This operation involves reflection through a plane perpendicular to A axis followed by translation along B axis by half unit and along C axis by half unit. That means in the previous cases you had to translate along only one axis by half units, but here you have to translate along two axes in both cases by half units each. Okay, so for likewise N glide perpendicular to A, we can also have N glide perpendicular to B and N glide perpendicular to C also. And the projection, stereographic projections of N glide perpendicular to A is repeated here. How? If O plus, suppose this is the B axis, this is the C axis, so the A plane is actually the plane of the paper or plane of your monitor, of your computer or mobile. Okay, so the axis is here on this point and it is perpendicular to the plane of the paper. So this O plus, if it is reflected through the A plane, then it becomes O minus. Now glide this, that means you have to translate this O minus along B axis by half unit and along C axis by half unit. On translating along B axis by half unit, it comes here, and then translating along C axis by half unit, it comes here. So this point is repeated here. Again, after operating the same symmetry element, this point is repeated here. So this is N glide perpendicular to A. So we can have 3. So in total we have 6 plus 3, 9. Now 3 more you have. And these 3 are D glide perpendicular to A, D glide perpendicular to B and D glide perpendicular to C. If you take for example D glide perpendicular to A, the operations are all same, but the translation instead of instead of half you have to translate by 1/4 unit. So these two operations are almost same, but here the translations are taking place by half units in both axes, and here the translations are taken by 1/4 units by both axes. So what about the stereographic projections? This is the stereographic projections. Okay, D glide perpendicular to A. So this point O, after reflection it becomes O minus, then 1/4 along B, 1/4 along B, 1/4 along C. O negative becomes O positive after reflection, then O positive after gliding half unit by B, 1/4 unit by B, 1/4 unit by C along C. Okay, so this is repeated here, this is repeated here, this is repeated here, and this is repeated here. Similarly, we can have D glide B and D glide C. So here also 3 symmetry elements. So in total it becomes 6 plus 3 plus 3, 12 glide planes. Now the 6th symmetry element, which is internal in nature, is screw axis. Screw axes are of 11 types: 2 1 3 1 3 2 4 1 4 2 4 3 6 1 6 2 6 3 6 4 and 6 5. So 11 set of screw axes for each axis. For A axis there are 11 set, for B axis 11, C axis 11. Overall there are 33 number of screw axes. If the screw axis is RD parallel to B, RD screw parallel to B, then it involves the following two operations: rotation by the reciprocal of R into twice pi, that means 2 pi by R, about this axis, B axis, and then translation along B axis by D by R into B unit. Let's elaborate for 2 1 B case. So it is 2 1 screw parallel to B symmetry element. Then the operation involves reciprocal of 2, that means half into twice pi. Then D by R, that is 1 by 2, that means again it is half into B along B axis. So rotation followed by translation. What about the stereographic projection? This is the lattice point. After having rotated along B axis by 180 degree, this is its virtual position. Then after translating along B axis, this is its final position, and this one, if is repeated here, then this element is 2 1 parallel to B screw axis. And if there would have been some lattice point here, then this one would have been repeated here and this one would have been repeated here. So this bolt point being repeated here, this bolt point being repeated here. O plus becomes O minus here, and O minus becomes O plus here. Similarly, this O minus becomes O plus here, and this O plus becomes O minus here. So this is about 2 1 parallel to B, 2 1 screw parallel to B. Let's elaborate this with another example. Suppose take, for example, it is 3 by 3 2 screw parallel to B axis. So if it is 3 2 parallel to B, then the operation should be the reciprocal of 3 into twice pi, that is 1/3 twice pi, that is 120 degree rotation along B axis. Then translation by D by R, that is 2 by 3 into B axis. Okay, so this is the difference. You have to take the reciprocal of 3 and then translate by 2 by 3 unit along B axis. Okay, so this operation is 3 2 screw parallel to B axis. So that's all about the symmetry elements. Now let us discuss one question here. A cube has how many threefold axes or axes of symmetry? So you have to recall the amazing fact where it is said that their product is always 12. N into A is always 12. N, if N is the number of what I say, if A number of n fold axes of symmetry in a cube, then N into A equals to always 12. So you are asked here how many threefold axes. So the value is of N is 3. Okay, then what is the value of A? Now the value of A is 12 by 3 equals to 4. So number of threefold axis is 4. The correct answer is 4. So that's all about the 6 symmetry elements, out of which 4 are external in nature and 2 are internal in nature. Thank you and have a nice day.